Finally, a section I'd like to call Fun with Math. In other words, expectation value revisited. The expectation value was the fourth postulate in our discussion of quantum mechanical postulates. And I want to answer the question, suppose I used the approximate wave function x times 1 minus x over a. If I look at a graph of that, it looks an awful lot like sine. Actually, it's very close to sine. And this is an approximate function. I've already normalized it. The normalization factor is 30 over a to the third to the 1/2. We remember that our expectation value, we're going to find a couple of interesting things out on this, besides doing a lot of fun math. Our expectation value is the integral of psi h operating on psi dx over psi star psi dx. Since I've already normalized this, this is just 1. So I can eliminate that right off. So, what do I need to do? I'm going to start with h operating on psi. Excuse me, I have to work on, this is going to be phi, is going to be equal to minus h bar squared over 2m second derivative of 30 over a to the third to the 1/2 x 1 minus x over a. Okay, so what I'm going to do is I'm going to do a little bit of reorganizing here. I'm going to pull the constants out. And so this is equal to minus h bar squared over 2m, 30 over a to the third to the 1/2, second derivative, and now piecing things together, I'm going to write this as x minus 1 over a x squared. Well, why do I do it this way? Well, it's pretty simple. What's going to happen is, what's the second derivative of the first term? The second derivative of the first term is going to give me 0. First derivative will give me 1, second derivative will give me 0. The second derivative of the second term is going to be equal to minus 2 over a. And so I now have equal to minus h bar squared over 2m, 30 over a cubed to the 1/2 minus 2 over a. I can do some canceling. My 2's cancel. Okay. And consolidate terms. This is going to be a to the 5th down here. And so this will be, and my minus signs will cancel. So this is going to be equal to h bar squared over m, 30 over a to the 5th to the 1/2. That's h psi. Now, what is, remember that expectation value of E is equal to the integral 0 to a of phi h phi dx, which is equal to integral from 0 to a of 30 over a to the third to the 1/2. This term here, which is just a constant, h bar squared over m, 30 over a to the 5th to the 1/2. Oops. I'm sorry, I forgot something. I forgot the wave function here. So looking at psi again is going to give me x minus 1 over a x squared. Now I can put in my constants. H bar squared over m, 30 over a to the 5th to the 1/2 dx. Okay. Most of that is just constants, so let's pull the constants out. I'm going to have two integrals equal to 30 over a to the third to the 1/2 h bar squared over m 30 over a to the fifth to the 1/2. I'm going to leave that for now. Integral from 0 to a x minus 1 over a x squared dx. That looks a little bit easier, doesn't it? This is a square, by the way. I'm going to take this and turn this into two integrals. The integral from 0 to a of x minus 1 over a x squared dx is just equal to integral from 0 to a of x dx minus 1 over a, the integral of x squared dx. This is just the integral of x squared over 2, evaluated from 0 to a, is equal to a squared over 2. This is just 1 over a integral of x to the third over 3, evaluated from 0 to a, is equal to a to the third over 3 times 1 over a, so a to the third, a squared, so this is a squared to the third with a minus sign. The result is that all of this together, a squared over 2 minus a squared over 3 is equal to a squared over 6. That's all this integral is. Now let's put it together. My expectation value of E is equal to 30 over a to the third to the 1/2. I'm going to group terms. 30 over a to the fifth to the 1/2. H bar squared over m, a squared over 6. What is all of this together? Well, this 30 times 30, square root of each is just 30. A to the fifth times a to the eighth is a to the eighth to the 1/2 is a to the fourth. So those two terms will give me 30 over a to the fourth. H bar squared over m, a squared over 6, and I'm going to cross this off. I'm going to call this squared. I'm going to cross these off. This is equal to 5. This is 1. The result is that I'm going to have let's see, I'm having some troubles doing my math right here. This is going to give me 5 h bar squared over m a squared. Now, I need to remember that h bar is equal to h over 2 pi. So I'm going to put that in. So this expectation value of E, I'm running out of room, equal to 5h 1 over 2 pi squared over ma squared. And what I will end up with is equal to, if I do this correctly, it's going to be equal to 1 point, I'm going to say I'll leave this as an exercise to the reader, 1.013 times E1, where E1 is equal to h squared over 8ma squared. The energy, turns out, is just a small amount higher than the actual energy of the first level. And that's something that we'll see later we call the variational principle. The variational principle states that the energy of any approximate wave function is going to be, must be higher than the ground.